All right, so we've seen the technique separation of variables, which sometimes works and sometimes doesn't. For a first order differential equation, sometimes you can separate variables and then it's a usable technique, and sometimes not. And before I end the lecture for today, I want to look at some examples where it does end up being helpful. So suppose you have an object and you're interested in tracking its temperature over time. So big T will stand for temperature of the object, and little t is time. So this is temperature of object. Using some, I don't know, Fahrenheit or Celsius. You need to get the units down when you're doing a specific problem, but we don't really need to specify right now. And the object is sitting in some environment, and we assume that the environment has a fixed constant environment temperature. So you can assume that the environment is kind of large. So it's not like two objects where they're influencing each other's temperature. No, it's an object and a huge environment. And the object's temperature is influenced by the environment's temperature, but not the other way around. So if the object is colder than its environment, then the environment will heat it up. And if the object is hotter than its environment, then the environment will cool it down. And Newton's law of cooling is one model that allows you to describe how the temperature of the object changes in time. So let's write down this differential equation. This law is going to be a differential equation. So here's the law. The time rate of change of the temperature of the object equals minus, and then some constant, and this is a positive constant, times the temperature minus the environment temperature. So the unknown function here is capital T of little t. So if I'm being less lazy, then I should write capital T of little t. And this is a constant, T sub E. And I mean, maybe you're less used to seeing a differential equation written out with the unknown function being called capital T, then you could always write it as x prime equals minus h, x minus, and then you could call this constant anything, but let me just keep the name TE. So this is the format of differential equation that we're looking at. But let me stick to the original naming. So this is Newton's law of cooling, and let's interpret this. Why would this be a sensible law for how the temperature of the object behaves? Well, if the object is hot, so focus on this difference here. This is the difference between the object temperature and the environment temperature. Positive when the object is hotter than the environment, and negative when the object is colder. And this is just some positive constant. So that's just going to scale that somehow. And let's think about what this law says about the way temperature is going to change. Whether temperature will increase, decrease, and how fast. So suppose you have an object that's much hotter than its environment. Let's just imagine some different situations. Okay, so there's my depiction of an object, and this blob is the environment that it's swimming in. And the object is now red hot, and it's so hot that it's like radiating all this heat. So what we would think in this situation is, since the object is much hotter than its environment, it should cool down quickly. It should lose heat quickly, and its temperature should drop quickly. And the law does say this, because if the object is much hotter than its environment, then T minus TE is going to be very positive, right? One way to say very positive is like 2 greater than symbols, maybe. It's a very large number. And then minus a positive number times T minus TE will be very negative, right? Because it's a negative number times a very large positive number. So then, and this is what the differential equation says is the time rate of change of the temperature. So in other words, the rate of change of the temperature in time is very negative. The temperature drops very quickly. Hopefully this makes sense. And if we had some object that was only a little bit hotter than its environment, so maybe I could depict that like this, without the rays coming out of it, then this difference would be just a little bit positive. And so this would, by the same kind of reasoning, end up being just a little bit negative. So the object would cool down, but more slowly. And hopefully that makes sense. You know, if I have like a cup of really hot coffee sitting in the room, then initially when the coffee is very, very hot, it loses temperature quickly, so the temperature drops quickly. But when the coffee is just a little bit more hot than the room, it's not going to drop as quickly. And this continues to work when you have this T being less than T sub E. So if your object is cold like this, like an ice cube or something, then it's colder than its environment, then that means T minus TE is going to be negative. And if it's very, very cold, then this would be very, very negative. And then a negative number, minus H, times this negative number is going to be positive. And so that we're saying that the temperature will increase. The time rate of change of capital T will be positive, so the temperature will increase. So the environment then heats up the object, and melts the ice. So basically you can think of Newton's law of cooling as something really simple. It's just saying that the rate of change of temperature is the rate at which an object's temperature attempts to go towards its environment temperature is proportional to the difference between the object temperature and the environment temperature. And the proportionality constant is H. And the minus sign just serves to ensure that object temperature always tends to go towards environment temperature rather than running away from environment temperature. Okay, so much for the law. Hopefully the law is now sensible. Now for the Math 4b part of things. Here's our differential equation. Let's use it to do something. So, or rather, let's just solve it. We can solve this in general. And we can use separation of variables. So can I write this in such a way that the right-hand side looks like stuff involving only capital T? So this is my goal, is I want to write it like this. The right-hand side is some function g of capital T times some function h of little t. So something involving only capital T times something involving only little t. Yes, in fact, it's already written like that because there are no little t's on the right-hand side. So this is already separated. Not only is it separable, it's separated. There are no little t's. So I can carry out separation of variables, no problem. If you want, you can think of this as being multiplied by 1, and 1 is the function involving only little t that it's multiplied by. So the way separation of variables works is it says now divide by your function of big T on the right side. Like that. So now I have stuff involving only big T here, and stuff involving only little t, and in fact not even involving anything, not even involving little t on the right side. And you know, actually, I find it more simple. So when I do this integral on the left side, I'm about to integrate, right? When I integrate on the left side, it's going to be super annoying to deal with how many minus signs there are here. So I'm just going to leave that h on the right side there with its minus sign. That way there's less chain rule crap to worry about as I integrate. And I'm less likely to make a mistake. Okay, so it's still true that this stuff does not involve big T. It only involves little t, and in fact, not even little t. Now, integrate both sides with respect to little t. So I get, well, let's do the right side. The right side is easier. That's just minus h t, and there's a plus c. And the left side will also have a plus c, but I only need to put the plus c on one side. And then as I work out the left side, I get log t minus t sub e plus c. And, oh, I forgot to point out, we did this, and the integration became an integral with respect to big T. So that is how that happened. All right, and we're almost there. Now, I want to solve for big T. That was the ultimate goal, right? So let's do that. Exponentiate both sides. And you've seen this done a few times now. Instead of putting the constant there, let me multiply by a newly named constant. And there's the solution for Newton's law of cooling. This is how the temperature behaves. So this is the general solution to the original differential equation. Now, if I give you some initial conditions, like if I say, okay, my object was this cup of coffee that I had sitting in the room, and at time 0, at time 0, the coffee had temperature 100 degrees. And if I tell you what h is, so h is a constant that I haven't specified, I just said the law just gives you this proportionality. So I'd have to tell you, like, the properties of coffee and how it interacts with air are such that h equals such and such. Then you could use my initial condition to figure out what d is. And for the environment temperature, you would have to put in I'd have to tell you what the room temperature is. Then you can make predictions. So to get this to be a particular solution, you need an initial condition to figure out what is d. All right, let's do an actual exercise with numbers. So this is one that I pulled from the textbook. So you've got a pan of water at a certain initial temperature, and it's put into a fridge environment. And 10 minutes later, you check the temperature, and then 10 minutes later, you check the temperature again. So you've got these 3 temperature readings. And then the question is, what's the temperature in the fridge? Okay, so maybe this is not what you immediately expected when you thought, let's look at an example problem. Maybe you expected a situation where I tell you, here's what h is, here's what TE is, now solve the differential equation, and go give me a prediction as to what the temperature of my object is at such and such a time. Tell me what it is. Sure, we can do stuff like that, but we can have partial information in any number of ways and find ourselves having to piece together our partial information and the law, which is a differential equation, the Newton's law of cooling in this case, and fill in the gaps and figure something out. Okay, so this is maybe I guess a typical situation. Okay, so we had our solution from before. We solved Newton's law of cooling, so we knew that no matter what the situation was, we had this for our general solution. So I'm going to give you one way to think about this, but it's not really the best way, but it's a decent way. And what was this? A minus ht. So this is telling us temperature of object, temperature of environment. In this case, that's a temperature in the fridge. That's what we want. So we want We want to know what this is. This constant is actually the unknown in the problem. And what else do we have? This is not known, right? It's going to take a specific value for our situation here. And also h here is not known. We're not told what is the coefficient of cooling or whatever this thing is called. We're not told what this is in the problem. What are we told? We want to know this. There are a couple of unknown things. And what are we told? We're told that, so like I said, didn't make this clear. I'm assuming that this is the temperature of the pan of water. In degrees C, because that's what the problem uses. We're told that T of a certain time is 46 degrees. It's 46. And T of a time 10 minutes later, so whatever time I put in plus 10, is 39. And T of 10 minutes after that, so whatever was the initial one plus 20 minutes, is going to be 33. And by the way, I guess I should make it clear that now this is in minutes. But when you say what... Sorry, I can't spell minutes. When you say what T is, when you give the definition of T, it's not enough to just give units. You should also say what T equals 0 represents. So time in minutes measured from what reference point, right? Time since what? And you can actually choose that reference point just like you can choose the units for the convenience of the problem that you're working on. And so why not just choose the reference point so that this is 0? So we'll make it time since the pan was initially put into the fridge. So T will be time in minutes since pan went into fridge. That's what little t will be. So then big T of little t is the temperature in degrees Celsius at the time given in minutes since the pan went into the fridge. And here we've got a 0 at 0 minutes, so the instant it goes into the fridge, we're told 46, and then now this is 0. So let me organize that better. So 10 minutes later, 10 minutes later after 0, we have 39, and 20 minutes after 0, 10 minutes after the 10, we have 33. So if you know the solution, this is the solution, it just has a bunch of unknowns in it. If you know the form of the solution, then if you want to, you could just write these 3 equations down, right? This is just 3 equations. So for this one, I would just plug in 0 for t and then write down, set it equal to 46. This one, plug in 10 for little t here and then set it equal to 39. This one, plug in 20 for little t, set it equal to 33. That's 3 equations. That gives you 3 equations, and there are 3 unknowns, right? This, and this, the unknown that we actually want in the end. So that seems doable. Maybe the algebra will be complicated, I don't know. But 3 equations and 3 unknowns, that seems pretty doable. Okay, so here I'm just showing you a way of thinking about the problem. A good way to approach it if you have had algebra, or if you've studied algebra, but maybe not differential equations. But here in differential equations, we can use the law directly to make use of the information in the problem. So I want to show you how we can do that. Okay, so same setup. T will be the time in minutes since the pan was put into the fridge. T sub E will be the fridge temperature. That's the environment that the pan is in, is the fridge. And T of T will be pan temperature at time T. So exactly the same setup as before so far. But this time I'm not going to rely on the solution to the differential equation. I'm going to rely on the original differential equation. So I'm going to use Newton's law of cooling itself. Rate of change of the temperature of the pan equals minus this positive constant times the difference between the pan temperature and the fridge temperature. And the goal is to get the fridge temperature. Now this, we saw that this is a separable differential equation. So I'm going to separate, but not to just go and solve. So I'm not going to go all the way. I'm only going to separate. And, you know, like last time, I actually prefer putting that h over there, just so that when I do start doing integrals, I don't make so many mistakes with minus signs. And I'm actually going to split up the d big T and d little t. Like I mentioned last time, that's a way of skipping some steps in the change of variables in your integration. Okay, so let me move this down. So we can see almost everything that we need. All right, so the kind of information we're told. So this is a very nice and usable form for the differential equation. So this, you can think of this as just another way of writing down Newton's law of cooling, and is telling you how changes in one variable correspond to changes in another variable. That's ultimately what a differential equation is. So it's telling you little changes in time are going to be related to little changes in temperature according to this equation. It's the exact version of what you could approximate like this if you put delta T and thought of them as actual little differences in temperature and differences in time. So this would be an approximation to it. Now, we are told that when little t runs from okay, so trying to find a good way to explain this. So what I want to do is use definite integrals to combine this information and make use of it directly without having to solve for what big T is and then do a bunch of algebra after that. So I'm going to put on some integral symbols, but I'm not finished. They're going to end up being definite integrals. So I'm going to put stuff here, 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 and here. That's what I mean by definite integrals. So this equality of differentials was true. Therefore, this equality of integrals will be true as long as I fill in times and temperatures that are in correspondence. So if I add this up from, integrate. If I integrate from little t equals 0 to little t equals 10 minutes, then over here, that corresponds to big T running from 46 degrees to 39 degrees. And also, I know that if I run this from little t equals 10 to little t equals 20, then big T, when little t is 10, that corresponds to big T equals 39. And when little t is 20, that corresponds to big T is 33. Okay, so these two equations now contain all the information that was in the problem, in the original problem. And I'm just going to make use of these two equations with the definite integrals. All right, so if you know what to do in order to finish the problem and find the environment temperature, you can go ahead and do it. You don't have to watch the rest of the video. But the rest is just going to be piecing things together and finally getting at the answer. What is TE? All right, so over here, actually the two right-hand sides are the same, because this one is is minus HT evaluated from 0 to 10, which will be minus 10H. This one will be minus HT evaluated from 10 to 20, which will also be minus 10H. So I get minus 10H here and here. So that's evaluating this integral and this integral. Now what about these two? So let me work on this one first. So I should get, when I integrate this, for my antiderivative, I get log of t minus te, and then I'm going to evaluate that from 46 to 39. That means I get log 39 minus te minus log 46 minus te. So that's log 39 minus te divided by 46 minus te. Okay, so let's remember that. That is what I got for this portion. And this portion I'm going to get the same thing, except with the numbers different, right? So I got that down there. And for this portion over here, I will get the same thing, but with the numbers a little different. So I get log, and then a number minus te divided by a number minus te. And let me go back. What are the numbers? 39 and 33. So how did this work again? I think 33 at the top, right? Cool. Now I have this thing equals minus 10h, this thing equals minus 10h. I actually don't care about h, right? In this problem, I don't really want to compute h. Depending on how you do the problem, you might need to compute h just to get it as like an intermediary step in order to compute other things. But I don't specifically care about h for its own sake. I only care about computing what is T sub e. Remember, the original question was estimating the temperature in the fridge. So nicely, I can immediately eliminate h. This thing equals minus 10h, and this thing equals minus 10h. So just get rid of the h. These two things are equal. The blue boxed in thing and the green boxed in thing. They're both minus 10h. So they're equal. So after we computed the integrals, these two things are equal. The log of this and the log of that are equal. Now, we've ended up with this equality. Now exponentiate both sides. That gets rid of the log. So I have this equation now with only one unknown, T sub e. So I should be able to solve this. It's one equation with one unknown. So let's see. So multiplying both sides by 46 minus TE and by 39 minus TE, I get that. All right, it looks like I'm going to get a quadratic formula, a quadratic polynomial in TE. So a quadratic equation in TE, and I just need to find the roots, because this stuff is going to give some TE squared type things, and this stuff, or actually maybe not, because the right side gives me a TE squared as the leading term, and the left side does too, and those would cancel. So yeah, maybe I'll continue So 33 times 46 minus 33 plus 46 TE plus TE squared equals, and then over here, 39 squared minus 2 times 39 TE plus TE squared. So these cancel. And the rest is algebra, so how about I just skip that? Or, you know, what might be more interesting is if I just show you how to get Mathematica to solve it. So this is meant to encourage you to use Mathematica to speed up doing your homework. Alright, so here I've got 33. You know, I'm just going to put in the original equation rather than the one where I possibly made mistakes. So I've got 33 minus, and then let's just call it TE, times 46 minus TE equals, and I have to put two equal signs to say that I'm making an equality statement here. Squared, and then solve that. And solve it with respect to TE, meaning tell me what values of TE solve this. So here we go. -3. Interesting. -3. So that must be the temperature in the fridge. So we end up with okay, so that was the temperature in the fridge, is -3 degrees Celsius. I hope that's right. I don't know. I mean, a mistake could have happened anywhere, but sounds reasonable that could be a temperature in a fridge. And I guess the main lesson is, you know, you can make use of the differential equation directly to put in information that you're given in a problem by taking definite integrals, rather than just always going general solution and then plug in initial conditions, get a particular solution, and then use the particular solution. So this is just an alternative method. It's really a matter of taste. You can do it in any way that you want.